Welcome to another class of analysis of Boolean functions. And today's class, we continue with complexity. And today we'll explore some randomized complexity measures and also some quantum complexity measures related with quantum computing. So in this lecture, we'll just touch a little bit about quantum computations. And quantum algorithms. Okay, so let me share my screen. Okay, so in the last class, we saw a bunch of things like decision tree complexity, the sensitivity, complexity, block sensitivity, certificate, and randomized decision tree complexity, and all these sort of things. And today we're going to see a bunch more. And we also saw a bunch of relations between these complexity measures. And we have this sort of a grand pseudo conjecture, which is sort of an implicit attempt to, which basically says that all these complexity measures should be somehow polynomially related. That's yet not true so far. We're going to see a table in a moment. However, there is a lot of progress in that direction. So another complexity measure we will see today is, I guess it's the 7th complexity measure so far, that I give you a polynomial, P, say from Rn to R, and suppose you have a function Okay, so remember, this guy is just 0, 1 raised to the n. So a polynomial P, say, approximates f if P of x minus f of x is less or equal than 1/3 for every x in here, okay? Okay, and so the degree of complexity of f is the minimum of all p's that approximate f of the degree of p. Okay, so for instance, so f has a multilinear expansion. We already saw that. And then if we use the multilinear expansion of f, that's a polynomial of degree, exactly the degree of f, which approximates f even with 0, actually. You can 0 here because it's identical. And so we definitely have that this is less or equal than the degree of f. Okay. So I'm putting these things as lemmas, so let me put lemma. Sort of an obvious lemma. Okay, and it's actually, for instance, as an exercise, we actually have, so the degree, for instance, of the OR of just 2 variables is 2, but the degree tilde of OR of 2 variables is actually 1. But they can be strictly less. So this is an exercise for you. So it's actually, you can do it in your head, actually. And why 1/3 here is basically because if you put anything less than a half, this is fine, because it's basically because you want to know that f of x is just rounding you round P of X, then that gives you the value of F. So that's basically the reason why we put a third, and it could be a quarter, anything less than a half, it's fine. Okay. So people usually use a third. Another, wait, let me see. Okay. So before I explain another complexity, let me give you some other lemmas. The first is that yes, the first is that this is due to reason in Sageti. That, and this would be a reading exercise, which is the block sensitivity of F is less or equal than 6 times the degree tilde of F squared. And I will tell you where this is. This is in lemma 3.8 of the paper of it's not the same paper we're following in this lecture, but it has a lot of nice on the degree of Boolean functions as real polynomials. Okay, by these two guys. Okay, so this is a reading exercise for you. It's actually a very simple lemma. You could just go there and read it. Yes. What else? So if that is true, okay, you check, and then as a corollary of that lemma, because we have lower. So we in the previous class we came up with a bunch of lower bounds. For instance, we do know that a block sensitivity of F cubed is greater or equal than decision tree complexity. And decision tree complexity we saw is very easily bounds the degree of the function, because from a tree that computes F, you can write a polynomial that computes F, and that polynomial will have degree at most the height of the tree. And so you have that. And so in particular, if that is true, then the degree of F tilde, say to the 6, is greater or equal than degree of F. Okay. And so degree and degree tilde are actually polynomially related. This is obvious, and this comes from, so this bound here we proved in the previous class. And so using that lemma here, we get this implication. And so degree and degree tilde are very closely related. 8. So now we start to see the randomized. We already saw in the previous lecture a randomized decision tree, which was, I even have the definition here at some point. Let me just recall you quickly. Block sensitivity, sensitivity. Yes, this randomized decision tree complexity. And that was, well, you have all these possible decision trees for a function, and then you come up, you choose a certain weighted sum, say a certain measure over the set of trees, okay? So it's a probability distribution, say. And then what is the randomized decision tree complexity? This is often denoted just as R of F in some places, and some other, even it's R of 0. So pay attention. And R of F is also used for some other thing in some other places. So since we don't still have like a unified notation everywhere, you have to, it seems that this R business is kind of depending on the taste of the author, which is fine. These things happened, and then they eventually evolved to some standardized notation. But basically what you do is you compute the expectation of the number of queries that you make to a particular input X, okay, over this probability measure. And you take worst case scenario, okay? So that will, under this probability measure, will bound the expectation, okay, by above, okay? And then you minimize over those probability measures, okay? That's the, that's randomized decision tree complexity. Let's learn another one, another randomized version. And this is related to this is what they call bounded error. Okay, so this is so what's the bounded or randomized decision tree complexity? So we already saw in the previous class that if you can come up with an algorithm to compute F, the maximum number of steps it takes to compute any input is equal to the depth of the decision tree associated to that algorithm. So doing algorithms to compute F and coming up with decision trees to compute F, they're basically the same. So we can use that analogy here. So so you take so let's say let A be a random algorithm to compute F. So basically what you can, you look at A as a sort of a implicit random variable, say omega, and that A, and for each W, A is a proper algorithm. So you can see A as a decision tree complexity that queries some of the components of your entry X and then guess what the value of F of X is. And it says F of X should be that. It's not guaranteed that it's going to be exactly equal to F of X. Okay, so for each omega, you have an algorithm, the algorithm guesses. You can put any input X here, and the algorithm guesses what's going to be the value of F. Okay, so there is intrinsic randomness in here, and it's dictated by the fact that this algorithm is actually a random variable, which is valued in the set of, say, partial decision trees. That's one way to look at it. Okay, and so then R2 of F is defined as the minima among all algorithms A of the worst case scenario, where you take the number of queries that A makes okay. Okay, number of queries that A makes. And so I give you some random variable, and then I give you X, say, and then you compute the number of queries that this algorithm makes to A, and you maximize over those, and then take the minimum over all these algorithm, randomized algorithms, say. And the constraint here, there's a constraint, of course, is that we say A compute F with a bounded error if the infimum over all the x's of the probability that A of x equals F of x, and the probability here is being done in this implicit omega variable, okay, which I will erase, if that infimum is greater or equal than 2/3. So you compute the probability that the algorithm is guessing right the value of F, and you take the worst, the minimum of all these guesses. If the probability is always at least greater or equal, I mean, another way of saying is that this works for every x. If the probability is always greater or equal than 2/3, then it's said to be a bounded error. Okay, so that's the definition. And so among all those algorithms that have bounded error, you take the maximum number of queries that A of x makes, okay? And so, so that's it. So what's the maximum number of queries here? Well, of course, that it depends on omega. So there is also the implicit maxima over omega here. And then once you have this worst case scenario, you minimize over all the possible algorithms. So this is the R2 here. And so R2 seems to have more or less, sometimes is written, sometimes is R of F. So in some papers, I see it as R of F. Some other places, I see it as R. So it's, again, sort of a confusing, but in any case. And we have the lemma, which is R2 of F is less or equal than RD T of F, the one we just saw above, and this is less than the decision tree of F. So this is, we already saw, because, well, this is randomized decision tree, this decision tree, and so this is trivial. We saw that in the previous class. And in here is also sort of a trivial, because if you imagine A to be a decision tree, a perfect decision tree, it will guess with like probability 1, actually. And so, and in here, you're actually measuring the height of that tree. And so therefore, you have this inequality. Okay. And then randomized, boundary over randomized decision tree, again, this inequality can be extracted for some functions. And simply because you're allowing yourself a bit more error here. Okay. And I'll leave this as an exercise, this step here. I just explain more or less how to do it, but I will leave it as an exercise. So we have this new randomized decision tree complexity. It seems kind of weird, but it's useful sometimes. So let me prove a lemma. The previous lemma was sort of obvious here and more or less obvious there, and this is an exercise for you. Let me prove some lemma, linking these two complexity measures I just gave. And well, so let A minimize R2 of F, okay? And so, so if you look at A as a decision tree, okay? So for each, it's a random is a random decision tree. So you're taking a particular decision tree according to an implicit probability distribution. Then let C, so let P be a path in A. Okay. So that's a random path as a thing, and CP be the set of H. Say the set. Let me work with F2 in this case. I think it has to be this guy. CP be the set that follow path P in A. So therefore, they will have the same value. But A, so even if they follow the same path, A will give you the same value. And so therefore, you can write the function P of X equals to the sum of the indicator of CP of X. And you just take A of CP because these have common values. Okay. So this guy is actually a random polynomial. Okay. And so what you can do is, and then what we know is that P of X is actually what A is doing. And so we do know that by definition, the probability of P of X being equal to F of X is greater or equal than 2/3 because P of X is just mimicking what A does. And so we can then use the expected value of P of X, which would be a polynomial. Again, a multilinear polynomial, because this guy is a multilinear polynomial with some random coefficients, and you're averaging those random coefficients. And you can just bound this by the expectation, because F is constant, doesn't depend on the variable, on the implicit random variable, which is in P here. So you can bound by this. And then what is that? Well, so F, so P is either 0, 1, and F is either 0, 1. So if they are equal, this is 0. And if they're different, this is 1. So this is equal to the probability of F being different from P. If they're different, it's going to be 1 exactly. So this is exactly equal to the probability of F being different from P, which we do know is less or equal than 1/3 because of that. So just created a polynomial that approximates F, which is this polynomial here, with 1/3, and that's why we got this inequality. Okay. So yeah, so another way, maybe another even better way to think about bounded error decision tree complexity is to think of a random polynomial that computes F with probability which has a bounded distance from F of 1/3, say, in this sort of an expectation of the value of P of X. This is another way of thinking about it. It's not exactly that because this is not an equality. However, it's sort of like this way. Okay, let me state another lemma. And the other lemma is the following. This is the block sensitivity is less or equal than 3 times the bounded error randomized decision tree complexity. And that I will put as a reading exercise is also pretty simple to do. We actually already did something similar. This is from 16 of the Berman paper that we follow in the previous lecture. Let me just put here so you can Google the name later on. What's here? Yes, that's the theorem from this paper here. Okay, so it's another nice, it's a half a page proof. Okay, all these proofs are sort of a half a page. It's not saying they're trivial, because you have to think a lot to come up with these proofs. And we will see proof of the sensitivity conjecture in the next lecture. And you see that it's a very simple proof, but although it was a very important problem, and it's the paper in the end also. So these things can, just because they look simple, it doesn't mean they are not important. Okay. So as a corollary of this, we have, well, we do know that block sensitivity of F cube is greater or equal than the decision tree of F. That we proved in the previous class. So therefore, the decision tree of F is also equal to 27 cube. Is you just have to take cube here. And this is important because this is randomized. This is sort of a randomized version of that. And we do already know this. And then this shows that they are polynomially related again. Okay. And this is sort of the end of the deterministic complexity measures. Now we will enter the quantum complexity measures. And for that point, I have to sort of explain a bit of what is quantum computing and what it is doing. Again, I'm not an expert in these things. I'm basically reading a lot of papers, coming up with my own understanding of things, and just dive in here and trying to explain what I understood so far. Again, it's partial, fresh knowledge. Perhaps we'll have a different point of view in the next lectures, and perhaps we explain things a bit different. But in any case, that's me trying to make sense of these things. So quantum. Okay, so what is quantum computing? It took me some time to actually wrap my mind around this, because people don't have the sort of a rigor you would expect in this field that a mathematician, like a pure mathematician like me, would expect. And so it's sort of hard to figure out things, but I think I got it more or less. So you have this, what is called the unit of computation, which is called a qubit, or more precisely, a 1 qubit. And that is just a superposition. So that is a superposition of two states, true and false, 0 and 1, plus or minus 1, of course. The notation is a bit different, so I will just follow the standard notation. And so it will be something of the form alpha naught, and then you have 0, and say alpha 1, and then you have 1. Okay, I'm following the cat notation here, cat for K-A-T, and these are cat vectors. So you just, I mean, this symbol could be replaced by, I don't know, your favorite musicians. This could be Clapton and this could be Hendrix. I don't know. They're just symbols. And the important thing is that we have, so alpha 0 and alpha 1 are complex numbers, and the squares add up to 1. Okay. And so this should be interpreted as the probability of seeing. So, okay, so alpha j is the amplitude, and alpha j squared is the probability of measuring, of observing, to be the right word, the state j. Okay, that's the idea here behind. And then in more generality, an n qubit is let's say a vector of the form, which have a certain summation. And now I have to choose a system because people use different notations here. Sometimes here they use numbers from 0 to 2 to the n minus 1. And sometimes they use x is just a vector in f2 of n. I will use that notation instead because we are in analysis of Boolean functions. So, okay, and of course, we have that equals 1. And again, the same thing, the probability, we can even update here. Alpha x is the amplitude, and alpha x squared is the probability of observing the state x. And what often happens is that people use interchangeably x as a binary string of zeros and ones, and the number it represents, the natural number, can be, it represents, if you read that binary string as the base 2 representation of a natural number. And so people use the same x for this, also the number and the string. This sometimes can be confusing. I will try to make not make that thing so it's a bit less confusing. And then we have these things. So if we measure the phi, so we see x, again, as I say, we see x with probability alpha x squared. And after measurement, so if you actually want to measure alpha x squared, actually know what their value is, the wave function collapses, you lose the information of all the other numbers, you just have that. So all the remaining information is lost. And why such a thing? They did experiments. That's how the world works at this small scales. So, okay, it's that intrinsic thing. If you measure a quantum system, then wave collapses, you know exactly what is happening, and so you lose the information of the possible other states that the system could be. Okay. And then if you don't want to lose information, you can apply, so apart from measurements, we can apply unitary transformations. Okay, say a unitary transformation, say U. That is, you just map phi to some other state. And well, this is a linear transformation. So if you write in the base states, oh, these guys here, I should write here. These x's are called base states. If you write again psi in base states, then it's a linear combination of the values of the other states of these alpha x's. So this is a linear operator. And you being unitary means u minus 1, the inverse, this operator is not singular and its inverse exists and it's just equal to its adjoint. Okay, that's what unitary means. Okay. And this can be achievable. This is done in practice, as far as I understood, by quantum gates. And these are unitary operators, but simplified ones. Like you can go to Wikipedia, type quantum gates, and you see a list of a bunch of things. And in general, you can build a unitary operator, a general unitary operator, but by applying systematically applying a bunch of these quantum gates. Okay, and they are very simple in nature, and etc. So in practice, it seems that you just apply, you create a system, let's say a computer that applies this bunch of quantum gates. And what they're really doing is just applying unitary transformation. And this can be done without loss of information, theoretically. Of course, that in the actual computer, you always have loss of information due to externalities, the construction of the computer itself, and the loss of information due to external noise. Maybe there is a train passing by that disturbs the computation. I don't know, or some sort of related thing. So there is also this field of quantum error correcting codes to in a way, reduce the loss of information in quantum computations, and it's still a very active field as far as I could understand, to come up with quantum correcting codes, just like we have in the standard computer error correcting codes, which are very good, and it's still in developing for quantum computers, as far as I could understand. Okay, and so we apply this bunch of unitary transformations, and what you can also what they call is a query. You can also query this, ask a question. Okay, and so what is a query? Query is going to be another unitary transformation, because these are all you can do, but of a special kind, and it is for a given x. Because in the end, what you want to do is you want to have an input x, which is a classical input, zeros and ones, and you want an output, which is also a classical output, just a 0 or no, true or false. And how you're going to actually input that thing into the quantum computer, and how you're going to output the 0 and 1. So the output, there are different ways to do it, but the input seems to be one way only, which is the following. So first I have to define this O of x, which they call queries. And so n here, so what's O of x? So I will give you some x in f2 of n, and n here is less or equal than capital N, okay? Some number in between, okay? And O will be a linear transformation that takes a state y into some other state. So you have to write that state as y1 be y2, and I'll explain what that means. And O would take that thing into Y1 and do a shore, which is exclusive OR, which they denote like this. And then you put xi here. So we have to tell you what I is, what coordinate are we choosing here. And then we keep y2 as it is. Okay. And then, so, okay, so y is a string. Is a string of bits. And so y1, b2, and y2 is just parts of that string. Y1 will be, so let me write. So y here, of course, y, yeah, maybe I should use y here. Is using the variable y there. So y here is, I'm changing x to y only, just to keep notation. Y, 1, y, 5. So okay, YF is a string of the size the quantum computer is, and then Y1 is a string of the size F to the ceiling of log n. Okay, B is just a bit, 0, 1, and Y2 is the remaining part. Okay, so you're splitting the string Y in 3 parts, one of size log of n, a bit, and the remaining part. Okay, and so what you're gonna do is the following. You're gonna choose I here, which was the I that it was in there, as to be what I called n of y1. And that means the number that y1 represents in base 2. Okay, so this is, by my definition, to 1 plus the summation of j equals, say, 1 to k of y1 coordinate j 2 to the j minus 1. Okay, so if y1 is, everything is 0, for instance, this thing is 0, and this is just 1. If y1, everything is 1, then this is what? This is 2 to the k minus 1, which this plus 1 is 2 to the k. Okay, but what is k? K would be this guy. Okay, so it'll be 2 to that number. But 2 to that number is exactly n if n is a power of 2. Okay, so usually we take n power of 2. Okay, so then the upper part of log n is exactly given, and this is exactly representing a number. This is exactly representing a number between 1 and n. And if it's not a power of 2, that's fine. It's just going to be less or equal than n, and that's fine. Okay. So n of y1 is just the number that that string represents. So there you go. That's the definition of this OX. It just separates in bit, and the first part just gives the address somehow, just like the address function in a way. Just give the address of the I bit I have to choose of the variable x, and then I do OR, then I do exclusive OR with this guy. And then remember that, who else me right here? 0, 1, 0, 1. The exclusive OR is what? 0. If 1 is 1, if one of them is 1, but if both of them is 1, then you put 0. If it was the OR, you will put 1 here, but it's not, it's the exclusive OR. So that's the thing for them. Okay, so that is what they call a query operator. And now we can describe a quantum decision tree. Well, in general, it's a quantum algorithm. What it is just A, which is a composition of you apply some unitary operators U. These can be any, but then you apply the same X. This is the same O of X, okay? So this is the attempt of the quantum computer to compute the variable X and to give an answer, okay? So that's, so a quantum algorithm A is this thing, okay? Or a quantum decision tree, if you like. And a computation is, and so we start with the state, the most simple state, which is this string with zeros. And the final state is phi, and that phi is just A applied to that guy. Okay. Of course, that guy depends on X. So this is the attempt of the quantum computer to compute the variable, computing input X. And now there is a 3 different ways of actually doing quantum measuring the output. And I will already write what they mean in terms of complexity. So the output is going to be 1 with probability. So the output is, you look at the, so this is the strings. So you can write, of course, this is the final state, and then let us write. This would be y, and y. Okay, so you look at those strings here, which end with 1, and those which end with 0. Okay, then those which end with 1, we have a cumulative probability, which would be the sum of the squares of those guys, of the alpha of those guys. That would give you the probability of being 1. And it's similar for 0. This is sum the strings which the alpha, the squares of the alpha of the strings that end with the strings that end with 0. That would be the probability of being 0. So 1 with probability. So the output would be 1 with probability summation of alpha y, where the last one is 1, and 0 with probability. I'm going to summate it over the guys that end with 0. Okay. And of course, the sum of these 2 numbers is 1, because the sum of all the numbers is always 1, because being unitary means that you always it's a isometric, which means that the L2 norm remains constant. So therefore, it started with 1 and will remain 1. So it's always a vector whose the sum of the squares adds up to 1. And so the sum of these 2 numbers is 1. Okay. And so what's the quantum complexity of a function f?
And E here stands for exact. Okay, so for each algorithm A, you have a T. And that is, say, the complexity of that quantum algorithm, the number of unitary transformations it actually uses. Okay, so that T here would be associated with the A. So I'm going to do the increment of the T of A. Okay, so it depends on the algorithm, over all the quantum algorithms A, such that it computes F exactly with probability 1, which means the sum of alpha y of x. Okay, so I give you x. Of course, x is given. And this, so in a way, the quantum algorithm is the collection, the order collection of these unitary transformations. And if you want to compute what it does in input x, you just put these queries in the middle. Okay. Yeah, this thing's continuous. It's always flipping between a unitary, a generic unitary, and this O guy. Okay, and so you have this algorithm. So you give an input x, and so in the end, I should rewrite here. This guy is, of course, a function of x. Okay, because I gave you x. So this is a of x. A of x. So it's a computed at x. So better to write it like this. A computed at x gives you that. And so you apply x to 0, and that's the output. You can write in the basis states, and then so the coefficients, the amplitudes will depend on x. So that's why we're writing like that. And the probability of being that is this, and the probability of being that is this. Okay. So I give you a quantum algorithm, and such that if and then I sum over all the guys that give you exactly the value of f of x. Okay. So if f of x was 1, then I summate over all the ones. Okay. And to be exact means that this thing here equals 1. Then it computes exactly. Okay. So you minimize the height t over all the algorithms that compute exactly f, the quantum algorithm. That's exact quantum complexity. We have another one, which is Q2 of f, and that is what they call bounded error. So this is exact. Right. And that is bounded error. And what is bounded error? Again, you're going to minimize over the t's a quantum algorithm, and then such that the probability of guessing right the value of f is greater or equal than 2/3. Okay. And so that's bounded error. Again, similar to the deterministic version. And just as a curiosity, we won't actually work with that. We also have the Q0. And that is when you have introduced certain uncertainty. That's called zero error. Just looking for the name. And that's the infima. So that's more or less sort of T, where you have two alternatives. You measure the last two bits. If the second to last is 0, result is inconclusive. And if it's 1, that means that the last bit is actually has to compute F exactly. And so my take from it was that you have a quantum you have a quantum algorithm A such that the sum of equals f of x and yn minus 1 equals 1 is 1, or there is some y with yn minus 1 equals 0 and y of x different than 0. So if there is some yn which has some positive probability of happening, so there is a positive probability of the result being inconclusive, and then you regard as inconclusive. And otherwise, it's just 1. But if this sum is 1, of course, that all these guys are 0. And then if that sum is not 1, you requiring that. Okay, so that's anyway, that's the, we want to use these things. I think most of the cases QE and Q2 are the ones that people most use, and so this was just a curiosity, but there is also this other guy. In a very simple lemma is the following, that Q2 of F is lesser or equal than Q0 of F, lesser or equal than QE of F, lesser or equal than decision 3 of F. Well, this is kind of obvious because the decision 3 for F is a quantum algorithm with no randomness and no anything else, because it computes exactly the function. And so there is no probability of being right or wrong. Yes, and so this is sort of a trivial. And well, if you want exact and you go to this bit is also sort of a trivial because the first is exact and the other you assume some boundary error. So that's trivial as well. And this being in the middle is just because, well, whenever the exact, you have something exact, that is also a possible algorithm for here. And so therefore this guy has to be less or equal than that. And whenever you have such an algorithm for this, you definitely yeah, you definitely have also this guy here, because this is a well, this is sort of a weird Okay, I realize now that actually I didn't quite understand this thing actually. Let's just erase that example. Um, as you can see, these things are hard to understand because they're never made precise. And so sometimes it can be very annoying. So this is sort of a trivial, and we see more or less how you can do from that. But you can do it here. And this is definitely trivial because just bounded from precise is trivial. Okay. We have these two competing complexities. Is a complexity of quantum systems, a quantum algorithms. And let me just, before I go, let me just note something. So if you have a certain state, which has this, okay, suppose you have a certain state with this superposition of bits. If we apply O of X to say Y, I want to apply O of in this state phi, so I have to apply, because it's a linear operator, I have to apply each base state. What would be that guy? Well, it will be just, let's say, xi, y1, 1, y2, plus, let me maybe move this thing to here. So it would be like xi, y1, 1, y2, plus 1 minus xi, y1, 0, y2. And this will happen if a y can be split in y1, 0, and y2. If the bit in the middle is 0, then I'm going to apply an exclusive OR. And so if x1 is 1, this is going to be the state. And if x1 is 0, this is going to be the state. So this is the guy. And similarly, this would be 1 minus x1, y1, 1, y2, plus x, not x1, xi, y1, 0, y2. And this is if you can split y with a 1 bit in the middle. And so if you iterate that thing, you will realize that A applied in phi, as we saw, is going to be now, so A of x is going to be, can be split in this way, of course, and with these coefficients depending on x. But then you do know that alpha of x is a multilinear polynomial of degree less or equal than t, because you apply exactly t queries to x. So you have these guys, and whenever you move, so you can apply like, let's say twice xi, but whenever you have an xy squared, that's equals to xi. So you can simplify to a multilinear polynomial, and the degree will be at most the number of times you apply this thing. So most t, okay. And so therefore, if A is exact, this polynomial y belonging to f2n, such that yn equals f of x has to be f of x. Okay. And now this guy is a polynomial of degree at most 2t. Okay, so we have our first lemma that degree of f is less or equal than twice the exact quantum complexity of f. And as an exercise, this is also simple. I will let you to show that degree tilde of f is less or equal than twice q2 of f. Is a corollary of these lemmas. What's the decision tree of f? Okay, decision tree of f is less or equal, we showed, than twice the degree of f to the power 4. We showed that in the previous class. Okay, degree of f and decision tree are polynomially related, and that's one of them. And then, so if you raise this side to the power 4, what you get is 2 to the 5 QE of f to the power 4. So it's another corollary. We have the same thing for degree. Have the same thing for yes, this is less than degree of f to the power 4. However, let me see what I want to do. Okay, so that's not the string of inequalities. What we want is that decision tree of f, so less or equal than block sensitivity of f cubed. But block sensitivity of f is less or equal than degree tilde, because that was the reading exercise. I told you about degree tilde squared. So that would be 6 cubed and then degree tilde of f to the power 6. But the degree tilde of f is less or equal than 2 times 6 cubed q2 of f to the power 6. So there we go. These are the two inequalities. So this we showed in the previous class, and this was the reading exercise in the beginning of this class. And this is this other exercise, which is also simple to do. Okay, so you have these two inequalities. So what these are saying, corollary, any quantum algorithm to compute f, so for any quantum algorithm to compute s, there is a classical, I'll say f in time t, there is a classical algorithm that computes f in time O, so at most some constant times t to the power 6, right, which was the worst of these two powers. Okay, so that means that if you can compute, and if you can come up with a super fast quantum algorithm to compute something, there's guaranteed there is a classical algorithm that can do just as good, because polynomial relations in computer science are not seen as bad things. They're seen as good things. The bad things are when you have like some exponential time to compute something. That's the best. That's the bad thing here. And so this is some, let's say, some knockdown in the quantum algorithms world in a way, because although it can be hard to find these classical algorithms that would perform just as good, only losing some 6 power here, as the quantum algorithm, it could be hard to find as well. It also could be the case here, these functions are defining the whole Boolean set. They are quantum algorithms that are specialized for functions that are only defined in the partial subset, that is a subset of the full Hamming space. And therefore, we don't have such a corollary for those partial functions. And so maybe there is some pretty good gain in quantum computations anyway. As far as of now, things are quite still, as far as understood, quite unclear if quantum computation can really be like this next big thing in computer science, or it will be just reserved for very special applications, where it's very fine-tuned to do that certain specific task. Okay, that will remain to be seen. Okay, and just to finish, we are almost done here. I will put as a reading exercise. Let me put as a reading exercise the paper of Nizami Zagati. There's a very nice paper you should read. Is it someplace here? Yes. So you read that paper. And a nice theorem in that paper is the following: that the degree of any function is greater or equal than log n base 2 of n minus some constant log also base 2 of n if f depends on n variables. You have all the things needed to read that paper, and especially read that theorem. Basically uses the fact that the expectation of it's an induction argument, but the expectation of the derivative I of any function is greater or equal than 1 over 2 to the minus the degree of the function, and that's induction. But that is the influence of the variable I of f. And then we do know that the total influence, which is the sum of these influences, is going to be then greater or equal than n divided by the degree of f by this induction argument. But this is by Fourier expansion, the sum of s squared, which you saw that formula already, and that's less or equal than the degree of f. Then putting those things together, you can show that there exists some C positive such that degree of f is greater or equal than log 2 base n minus C log 2 of n log 2 of n. Okay, that's more or less the proof. And then we use this thing. Okay, it's a very nice paper. It has other things you can read, and I really recommend you to read that. And in the next class, we will dig into the sensitivity conjecture, and in the following ones, I'm still figuring out what we're gonna see. And I hope you enjoyed this class, and see you next time.